let's consider two impacting particles in the plane. So two particles that are impacting in the plane. During collision, so that's particle 1, particle 2, masses m1 and m2, velocities v1 and v2. The particles are gonna collide, and post-collision, they're gonna have velocities v1 prime and v2 prime. Given the pre-impact velocities of the particle, we want to determine their post-impact velocities. Given v1, v2, m1, m2, find v1 prime, v2 prime. And actually, v1 prime and v2 prime, that's two vector unknowns at the plane, right? Each v1 prime is a vector that has two components, v1 prime along ex and v1 prime along ey, for example. So these are basically four scalar unknowns. And to find these scalar unknowns, we need four scalar equations. Great. So where are these four scalar equations where are they gonna come from? Well, let us look at the free body diagrams of the particles during impact, and let us see if we can identify any conservations. So during impact, there are collision forces acting on the particles, and these forces are going to be along n. Remember, t is the tangent to the plane of impact and n is the normal to the plane of impact. So during the impact, we have impact forces acting on the particles, F and minus F, and F is along n. Okay, so for example, if I consider the system of the two particles combined, the sum of the external forces acting on these particles is equal to 0. So for 1 and 2 combined, F is equal to 0. The sum of the external forces is equal to 0, meaning that the linear momentum of this system pre and post collision is conserved. Okay, so we can write this statement, the balance of conservation of linear momentum. Basically, G, linear momentum pre-impact, is equal to G prime post-impact. And the linear momentum of the system of particles is the sum of the linear momenta of the constituents. So that's m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. Great! That's a vector equation in the plane that we can project along ex and ey, for example, to obtain, or we can project it along n and t equivalently to obtain two equations. 1, 2. I'm so happy we're making progress. So we have, again, 4 unknowns. We need 4 equations. We found 2 equations so far. Well, let us see. Can we find more equations? Can we find more conservations? So let me consider this particle on its own. Well, the sum of forces acting on particle 1 on its own is not 0, because F, the sum of forces acting on it is F, is not 0. But along the fixed direction t, the linear momentum of particle 1 is conserved. And the same applies for particle 1. For 1, its linear momentum is conserved along t. So we can write m1 v1 dot t is equal to m1 v1 prime dot t. So that's basically g1 dot t is equal to g1 prime dot t. Oh la la, that's a scalar equation. That's our equation 3. Okay, And we said the same applies for particle 2. For 2, so again, for 2 alone, linear momentum is conserved along t. So g2 dot t is equal to g2 prime dot t. 2 here does not denote a time, 2 denotes just particle 2, the system. So m2 v2 prime dot t is equal, v2 dot t is equal to m2 v2 prime dot t. Cool, so that's our fourth equations. But we have to be careful, we're not done, because I know that we have now 4 equations for unknowns, but we have to be very careful. These equations are not independent. Basically, this equation along t, when projected along t, is the sum of the other two, 3 and 4, right? So this equation 2 is equal to 3 plus 4. So these 4 equations are not independent. We need 4 independent equations to solve for the 4 unknowns. That's where our coefficient of restitution comes in. This equation that we derived last time, the coefficient of restitution, that's where it comes in. That's our fourth equation. 4. E is a scalar, v2 prime dot n minus v1 prime dot n over v1 dot n minus v2 dot n. This is our fourth equation, and that's an independent equation. So given the coefficient of restitution between the two particles, we can find their post-impact velocities.